Green. Okay, so as promised, I'm going to talk about how many of you have ever heard of this before? Constructible numbers? Actually, how many of you seen this in high school? Did they ever talk about? So when I took geometry in high school, my teacher actually had me do these contest tests, so it was actually kind of fun because I just sat around and worked problems. But one day, he came in and constructed a regular pentagon. Here, I'm going to show you how to construct a regular pentagon. And I watched it, and I was captivated. I thought this is fantastic. I can't believe this works. But he never told me anything about why. It was like he might as well have had one of those chef's suits on and an apron and just reading out of the cookbook, right? Do this, do that, and look, we've made a regular pentagon. Why does this work? This comes out of this constructible numbers too. When I say constructible, I mean constructible with a straight edge or an unmarked ruler and a compass. And no, not like the compass Johnny Depp had in Pirates of the Caribbean, but you guys have seen one of these, right? Compass, you've seen pictures, right? I can't believe you wouldn't recognize that beautiful picture, but it's got like, something that, you stick your lab partner with, and then this has a pencil on it, and you use it to draw circles, right? So, and of course, you don't get something for nothing, and a fixed beginning unit. So we have a line segment, it's a length segment line. So if I've got a 1, so I know that that's 1 long, and I've got these two tools, I've got a compass and I've got an unmarked ruler. What are the numbers that I can draw? And what I mean by draw is, can I construct something of length 2? Can I construct something of length 2/3? Can I construct something of length square root 2 or the cube root 2? Well, which ones can I get from this? Now, here are the rules. We got to make clear the rules because I don't think I made it clear yet. Classically, the compass was considered to be collapsible, right? So in other words, I can take the compass and draw a circle, but I can't use it to measure lengths, right? So in other words, I can't take the compass and put a point here and use the compass to make another length here. But yes, I can, and I'm going to. And the reason is it actually can be shown, and there's not enough time for me to do this now, but if anybody requests it later, I'll do it. You can transfer lengths only with the compass. So I am going to let the compass measure lengths because I'm a lazy man. And if I drew just a couple more circles, I could do it without the compass being able to preserve lengths. So when I say preserve lengths, what I mean is if I've got this, I'm going to allow this because it's equivalent to not allowing it. I can use my compass to measure that length and then draw a circle over here of that same radius so I can put this transferable length over there. Everybody okay with me? Also, my ruler is not only unmarked, but I can't mark on it. That one actually makes a big difference. I can't mark my ruler because actually it's going to turn out that for my beginning unit length, I can do, for example, the square root of 2. I can get that if you want to find out. I can't get the cube root of 2. With a marked ruler, I can get the cube root of 2. If I can mark on the ruler, I can go a little bit further. In fact, I can get the solution to any cubic or quartic equation. Okay, so those are the rules. I've got a compass and I can cheat and use it to preserve lengths, transfer lengths. And I've got my fixed, and I've got a ruler with no markings on it and I can't mark on it. And I've got this fixed length of 1. So let's start. I've got one. Can I get two? Somebody tell me how I can get two.
You put them next to each other.
Like put the pointy part of the compass here and the pencil here. Draw a circle, right? And the circle's radius 1. And now extend using your straight edge. And now you've got another 1, so you've got 2. Okay. Everybody okay with that? So now you see how we can get any positive integers, right? I can get 3 and 4, and I can just keep this process going and get me 1. By the way, I can also get negatives if I like. If I wanted to distinguish, I could say put an arrowhead on it. If it points to the right, it's positive. If it points to the left, it's negative. And treat it just like vectors or something like that. Okay, what else can I? So now, here's what we have so far. Now we have all positive integers. And if you wanted to do a vector direction, you could consider getting negatives as well. So that's what we got so far. Well, there's infinitely many things already, right? But there's more that we can do. Here's a couple of things that we can do. So constructible number. We can construct a plus. Everybody agree with that? Because I've got length A, length B, I can do my cheating thing and use the compass to extend A to B, and now I've got an A plus B, right? The same way that I built 2 from 1, just a little bit more general. And of course, we can also construct A minus B, or at least the absolute value, or we could call it negative and put the head on, right? So we can actually take differences with this as well. What else can we do? So there's some other tricks. Okay, this isn't really a number, but I am pointing out that we can cut an angle in half. And this will be useful later, for this technique at least. So suppose I have 2 line segments like this. How can I bisect that angle?
You draw an arc around both the ends, and then where the 2 arcs meet.
Okay, so you got to make it wide enough so the circles overlap. So maybe I better spread you out a little bit, right? And do the same thing here. And then you run it right through where the circles overlap. That's actually not too bad for me just guessing, but that's essentially, everybody see what we did, right? The 2 circles that overlap, you just run it right through the intersection points and cut the angle. Here's another thing we can do. So we can cut an angle in half. We can also get a perpendicular bisector. Well, let's say a perpendicular to a line segment. Through another point, either on or off the line segment given. We can also bisect the line segment as well. So let me explain how you do that. Suppose I have a line segment here, And suppose I have a point off the line, right? How would I get a perpendicular to that goes through this point?
Didn't you do the same thing, but use the end points of the line instead to make your circle and then draw the line to prove where they intersect?
Okay, so run that by me again.
Like draw a big circle on the left and right, and where they intersect, it would be the middle, and draw a line through that.
Okay, okay. So if we wanted to bisect, right, draw a wide enough circle so they overlap. And right now, take these 2 points where they overlap and use straight edge, all that. And if I draw that a little bit better, this is a bisector, but it's,
Now we can use that technique. We draw a circle around our isolated point such that it intersects the line segment 2 places.
Okay.
And then we use those 2 intersection points as like our where we bisect.
Right. So if you wanted to cut the line through this point here, you also draw a circle that's big enough so that it hits here, and I drew a double circle. I'm sorry about that. Draw a little bit shorter so it hits here and here, and now do the same thing here. Everybody okay with it? So we can draw a perpendicular bisector. In fact, we can do a perpendicular line through the point, actually on or off the line. And that's going to be useful. So what do we have so far? Well, we can cut angles in half. We can bisect lines to get a perpendicular to it. And we can get any number. Let's say a positive. We can get any number. But you can also get, if I have A and B, what else might I want to get? So I can get the sum of A and B. I might also want to get the product. So given constructible A, B, we can get also number 1, A plus B, and minus as well. And we can get A. We can get the product. And how can we do that? This is like a total blast from the past. This is about doing your trigonometry or your similar triangle. It's like let me draw a triangle for you. Actually, I'll do this first. Let's see how we can get A. Build a triangle this way. Let this be my length 1, my universal length 1 here. And let the length of the whole shebang here be B. And I drew the hypotenuse to soon here, I guess. So here's what we do. Length 1, length B, right? And we can do this. Take a length B, and then I'll take my universal length 1 out of it. Take this point here, draw a bisector of length A. Make it a length A. If it's too long, put your compass here because you can get length A, right? Now, perpendicular bisect, perpendicular through this point. Now draw this. This length right here is AB. Because you have to have similar triangles, right? And notice this is to this, quotient is B, as this is this, quotient is B. And so that allows me to construct AB. I made an assumption in this picture. What is it?
B is greater.
That's right. I assume B is greater than one. Well, it is possible that B is less than one, right? By the way, what if B equals one? Then I'm a Dorcas Malorcas for even thinking of my tools because I've already got right, 1 times A, right? So you just do a little role reversal here if B is less than one. So this is B is bigger than one. B is less than one. So what I would do in this situation is this is B. This is 1. And this sucker is A. So connect this and then do a perpendicular through this point, and this is AB in this case. Ratio here, 1 over B, ratio here, 1 over B. So now AB is 4. Everybody okay with that? So check a window. So now if I've got 2 lengths, I can get their product. How about their quotient? Right, that's right. It's role reversal. I mean, you can basically bootstrap quotient of product here. But for the sake of completeness here, I'll just write down what you do. Again, there's a couple of cases to consider. If B is bigger than 1, then what you want to do is this. Well, let me draw this piece by piece. So I want to draw this in the order in which I would get them. Let's go 1. B, A, do my perpendicular, length A. Connect this up, and this should be A over B. And in the case that B is less than 1, then my picture is B 1, and let's see, this time I'm going to have an A here. Drive this up, hit it with this perpendicular right here, and this length should be A over B. Yeah. A. Okay. So guess what? If I have any 2 constructible numbers, then I have their sum, their product, and their quotient. Right. So all rational numbers again construct. Again, assuming that the negatives are some kind of directional, we do it that way, but certainly all positive fractions. Like I say, I can get any fraction I want. It's kind of fascinating. Well, maybe that's it, right? But there's more. And in fact, when you see this, you might think, well, there's a whole bunch more, but actually, in a certain sense, at least very loosely, this is kind of the end of the road here. Given A bigger than 0, we can construct the square root. I can build the square root of A. That's kind of cool. And this one I don't think has any cases to it, so I'm digging on that. Here's how you do it. Let's suppose that you want the square root of A. So, you know what? Move it over here. Suppose we want to get the square root of A. I'll show you how to build it. This will be A. And this will be 1. So we can do that. Length A, then tack length 1 onto it. Find the center of this sucker, which we can get by bisecting the line segment, right? So the center is like, say, right about here. And use your compass to draw a semicircle, which I don't do very well, but it's okay. Everybody okay so far? Find the center, use the compass, draw a semicircle. And then from the joint point here, straight edge up here. Now, straight edge connect. Straight edge connect. By the way, just for giggles, what kind of triangle is the big one in here? It's always a right triangle. Any triangle inside a semicircle is right triangle. That has the radii, that 2 radii as endpoints and has an interior. It's right triangle, right? But the whole triangle, let's call this length X here. This whole triangle here, this one on the left is actually similar to the one on the right, isn't it? Right? Because they share the angle 90 degrees. This angle is the same as this angle, and this angle is the same as this angle, right? And so what that means is 1 is to X as X is to A, right? If you look at the similarity here, this is to this as this is to this. And so I get X squared is A. And there you go. So now I can give you the square root of any rational number as well. Square root of 3, square root of 4. And guess what? It goes further than that because I can construct the square root of 3, right? I can construct 5 plus the square root of 3, but then I can construct the square root of that. So I can give you the square root of 5 plus the square root of 3. Let me write down this identity because I don't want it to go past. It would actually get reasonably close to talking about the 5 con. But Gauss, how many of you have heard of Gauss? You hear about him in math, you hear about him in physics because he's always flexing them out. But Gauss famously around 1800 constructed the 17 gon. And guess why? Here's why. This identity just is too good to not be written down at high class. That is minus 160 plus 116 radical 17 plus 116 square root of 34 minus 2 radical 17 plus 1/8 times the square root of 17 plus 3 radical 17 minus square root of 34 minus 2 radical 17 minus 2 radical 34 plus 2 radical 17.
Of course.
But the important thing is this number is constructed, right? It's constructed. How would you do this? Imagine trying to figure out what this is on a calculator, right? If you were trying to build this number, the first thing you would do is you would probably take 17, take the square root of it. Well, I can build 17, and so I can build the square root of 17. So I'm going to multiply it by 2, which I can do because it's just adding this to itself. and then I add 34 to it, and then I take the square root of that. Double it, right? Then I do the same thing over here, right? Essentially, I construct this over here, and I construct 3 radical 17 equals 17, and I put this all together and get what I hope is a positive number. And then I take the square root of that, right? Take an eighth of it, not a problem. And then add it to all this other constructible stuff, and I get a big fat constructible number. This is constructible because it comes from a sequence of square roots. And in fact, for those of you, you don't really need this to go on with the talk, but for those of you that are big algebra fans, the field of all constructible numbers is basically all you could do it as iterating square roots this way. A number is constructible, it must have a minimal polynomial, it's a power of 2. This is an infinite field extension of the rationals, very, very big. But the reason this works, and why does this work, is every time you do a constructible number, when you do this, what are you doing? You're doing one of 3 things. You're intersecting 2 lines. And that's basically finding the solution to that is just dividing stuff. And that was a basic operation. Or you're intersecting a line and a circle, right? And what happens when you intersect a line and a circle? If you think back to high school, the equation you get is basically a quadratic equation. And all you need to do to get that is, the only thing different about a quadratic equation is get that pesky square root in there. Well, we can take square roots, right? And the other thing is intersecting 2 circles. And again, that's a quadratic equation. So really this covers everything that we can get. This is actually a very big field of numbers. There are all kinds of things, but guess what's not there? The cube root of 2. Right? You can't get the cube root of 2 from doing a successive quadratic extension. You can't extract square root, just even roots, and get the cube root of 2. Okay. Any questions so far? So, I promised, by the way, because of this, Gauss was able to construct a regular 17 gon. This is math club, not math purgatory. We will do the more modest 5. So the first thing is, okay, so let's think about what we've learned so far. We can do square roots and various things. What do we got to get? How do we go about it if we're going to try to construct a regular pentagon? Well, I'm going to have to do a little algebra, which is kind of, so I'll ask you all, how many of you all are comfortable with this? Because there's a number of ways you skin a cat. I need 5 points on the circle to get a regular pentagon, right? And it should occur every 72 degrees or 2 pi over 5. Everybody agree with that? So let's say this is about 72 degrees right there. So once I know where one of the vertices is on the pentagon, I know everything. Can somebody tell me why? How can I? So if I just happen to know where that first vertex is, the one in the first quadrant, that's not sitting on the x-axis. If I know that one, I've got enough to finish it off. How can I finish it off? Yeah.
Oh, yeah. You can like put the compass on the viewpoint, draw a circle around it.
Good.
And whenever it intersects.
See what a big cheater I am, right? I'm glad I did this, but of course, again, you don't. So use the compass here, put the point here, and then flip it over to do off the right circle, and then repeat this process. So the big question is, what is that? How do we get it, right? So the easiest way to do it, so I'll do that. I'll try the easiest way. So how many of you have ever seen this item? If you've had a good trigonometry course, I mean, like a really good trigonometry, you might have seen it, right? How many of you have had calculus? or anyhow too. You can actually prove this identity here, and of course, I is famous square root of minus one. You can actually, how many of you remember doing series, right? Are you still in therapy over that? Or do you remember the series? If you use the Taylor series expansion for e to the x, and you just very naively put an I theta to that, and use the fact that I is square root -1, it will naturally break up into the Maclaurin series for cosine, and then I times the Maclaurin series for sine. So that's kind of an easy way to see this work. So really, this point right here, in the so if we consider this x and the y axis, or you could just consider this y. So the y coordinate is, you can forget about the I if you like, but e to the I 2 pi over 5 to the 5th power is equal to e to the I 2 pi, which is what? 1. Everybody agree with that? Because theta is 1, so that's 1, 0. Everybody agree with that? But e to the I 2 power 5 is also equal to cosine 2 power 5 plus I sine 2 power 5. So it's precisely this point here. Because if you read what this says, it says, hey, Jim, my x-coordinate is cosine 2 pi over 5. And so if the radius of this circle is 1, which I didn't say, but I should have. I mean, you can scale it whatever you want. We'll make it 1 here. The x-coordinate is cosine 2 pi over 5. And the y-coordinate, the I, so lifts it up here, is sine 2 pi over 5. Okay. But see, this gives me an equation. If x is e to the I 2 pi over 5, then x to the 5th is equal to 1. So this is a root of the equation x to the 5th equals 1. By the way, there's an easy root of this. You guys see what it is? 1. Oh, and look at that. That's the point 1. Isn't it great how math always takes care of it? Right? So let's see if we can take apart this equation. So what we have is, so I'm trying to solve this here. So x minus 1 times x4 plus x cubed plus x squared plus x plus 1. Now, if you set this equal to 0, one solution you get is x equals 1, which corresponds to this point. That's garbage. We don't want it. We're looking for the 1 in the first quadrant. So e to the I 2 pi over 5 is a root of x4 plus x cubed plus x squared plus x1. But, oops, right? I mean, that's a 4th degree polynomial. There is a quartic formula that we could employ, but I'd rather eat dirt, right? Because it's awful, right? There's a simpler way to solve this. Let me draw a picture of what we expect to get here. This equation should govern, that's the 1 point. There should be 4 roots to that in the complex numbers, right? It's this 4th degree equation. And it should basically govern these other 4 roots. What can you say about those other 4 roots? Right. In particular, 1 should be the only real root of that. You should have 2 complex conjugate pairs, right? And in fact, here are the complex conjugate pairs. How many of you have heard that when you have a complex, or when you have if you have a polynomial with real coefficients, if it's got complex roots that aren't real, they have to come in conjugate pairs, right? So I spy two conjugate pairs here. This is going to help me. You know what? There's also a certain amount of symmetry to that. Wouldn't you guess? So I'm going to take a flyer here. I want to see if I can make this fly. Well, that's naive, right? Oh, guess what? The X4 works. Ding, 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 right? And the 1 works. But why did I choose -1 and -1? Right? That's another possibility. Right? But there's something about this that tells me that if I've got a pair that match on the end like that, it should be a pair of +1s and not a pair of -1s. Anybody see why that's true, or why that would have to be true? Eventually, I'm gonna have to solve this polynomial, right? Because the root we're seeking is, it's one, there are 4 roots here, 2 out of this, 2 out of this, and this is just one of them, right? That's right. If these were negative, what could you say about the solutions? Real. They have to be real, right? I don't expect these solutions to be real. So I should do this, right? If I'm gonna be guessing at this sort of thing, right? Let's see if I can make this work. Let's multiply this back. Let's see, the coefficient of my x cubed term. The coefficient of the quadratic term, 1 and 1 and AB. The coefficient of my linear term. That's a good sign, isn't it? Right? Right, okay, so
We got X squared a little bit.
oh, I forgot my x squared. I certainly did. So for this to work, I just need and right? And that looks like a quadratic equation after I sort everything out. Right? So if I combine this, I'm gonna let B equal 1 minus A. So at the end of the day, I guess I get the equation A squared minus A minus 1 is the big fat zero. Squared.
Isn't it A minus B squared?
Not really.
Oh,
I think I did there.
that's right. Yeah, I see.
Okay.
That's fee, right?
Was that?
That's fee. The golden number, that's fee, right?
You're golden. That's right. So what we get here is, well, I am going to get, and of course, there's also, well, right, this will give me A. So A is 1 plus or minus the square root of 1 and so it's 5 over 2. Which one? It doesn't matter, right?
Because B is the constant, so.
Yeah, say A is the positive, and B is actually the other one. And notice when you add these up, you get 1, so it's got to be right. Right, okay with it. Now, now remember, you seek I, 2I, 5, which is that one. I've got 2 quadratic equations which one is the appropriate one to use? So in other words, my quadratic equation is either x squared plus ax plus 1 or x squared plus bx plus 1. Which do I want to use to find the red one?
B.
I want to use B. How come?
Because if you use A, the two roots will have a real part negative.
Right. These two, in particular the red one, has a positive real part. These two have a negative real part. So so the one I want to use is x squared plus 1 minus radical 5 over 2x plus 1. Because if I use plus, the real part is the negative of this divided by 2, right? That's the real part. The crap under the square root turns out to be the imaginary part or whatever. The real part here will be positive because you're taking the minuses. But if you take the negative of this, it'll be negative, and it'll actually be the two that are on the left. All right, everybody okay with that? So set this equal to 0, and only one more question. Well, in this sequence. Square root of this squared, which I guess is 3 minus radical 5 over 2 minus 4. So that's minus 5, right? Over all of this, which is a mess. So this is radical 5 minus 1 over 4. Notice this thing under the square root is negative. That's good. So this is going to be plus 1, or let's say I over 2 times the square root of 5 plus radical 5. That's the answer, right?
Right.
Now, lucky me, I really only need this. So I really only need the real part, right? Because if you think about the circle here, if I know the real part of this complex number, this tells me the x coordinate, and this is essentially telling me the y coordinate. This is on the circle. I get the y coordinate for free. Now let me point out, I meant to point out earlier, that I do want the plus 1 because I want my y coordinate to be positive, right? It was the red point, but actually it doesn't matter that much because once I have the x coordinate, once I know that, all I got to do is go up here and find it, and there it is. Everybody follow that? So yeah.
If we manage to pick the second root, it doesn't matter even, right? Because we
No, it doesn't matter. I've been fixated on that other one. Actually, it doesn't matter what route you pick. You can kind of once you get one of them. But this is the easiest.
Yeah.
So you find vertex in first quadrant. Not this one on the x-axis. Need to construct length of radical 5 minus 1 over 4. And it's doable, right? Because a square root minus something minus something. So how will we do this? And this is, I don't even remember how my geometry teacher taught me how to do this. Well, I mean, he didn't really teach us how to do it. He just kind of did it for show. But this is why it works. So in constructing a regular pentagon, make the radius of your circle Oh, I'm gonna regret this already. Let me start over again here because I got where I was gonna go here. While we're here. Okay, so the radius of your circle is 1. So draw this circle radius 1. Now what I want to do, well, let me ask you this. How am I going to construct radical 5? And keep it kind of in the spirit of this. Well, right, radical 5. The easiest triangle I can think of will give me a radical 5. Notice that I've got a very convenient base length 1. And let's go 2 up like this. And this is square root of 5. All right. So let's do that. I'll draw a perpendicular bisector here. That's twice as long. I'm not quite sure I made it, but that was close. Perpendicular bisector is not the right word. Perpendicular line to x-axis going through one. Right? Length there. Measure off length 2 here, right? Now, what do we have here? This length is now square root of 5. Okay, how about radical 5 minus 1? How could I get that?
And just use our compass to put square root of 5 in the x-axis.
Right. This is length 1. Everybody agree with that? So do my compass here. So this is length 1 as well. So what's left over here is radical 5 minus 1. And the 4 is a very convenient number, right? Because all I have to do is cut this in half and cut it in half again. Right. So cut it in half once, cut it in half again. And this length right here should be my desired radical 5 minus 1. Right? Now I wanted that to be an x coordinate. So take the compass, complete the circle down here, and do a perpendicular bisector or perpendicular line up here. That should give you your 72. So there's your first piece. And then kind of mark it off. So, under there. And that'll give you your regular triangle, which it's not perfect, but not too sloppy since I didn't have any tools. Right? Okay, everybody see how we did that? All right. Any questions? All right, well, don't ever say I never gave you anything. What?
Yeah, I don't really get it how we bisect an angle.
Bisect an angle?
Yeah.
Oh, so an angle, let me see if I can draw this a little bit better. To bisect an angle, what you would do is so suppose you have something like this. So take your, we're going to use both of these points and draw overlapping circles here. The same radius. That's probably not overlap, is it? Let's try it. And same radius here. If I can do that. I don't know if I did that exactly right, but where they overlap here, yeah, that's my sloppy drawing. That should bisect the angle.
Why does that process work?
What's that?
Why that process work?
Let's see, what time is it? If you want to stay after the math club, we'll prove it.
Yeah, okay.
Yeah, I'll be happy to do that. You better be careful what you ask. I actually proved it like, it was a nightmare. Proved how the square root algorithm works, so. Yeah, but the process, you can see sort of intuitively that it works, but we could sit down and do something a lot more hardcore. But yeah, this bisects an angle, but in general, you can't, I mean, you can trisect some angles. You can trisect a 90-degree angle, for example, but a general angle, you cannot trisect it, so. Okay, other questions? All right, you all have a great weekend, and next week in the math club, well, I'm 90% sure we probably won't have a math club, but we'll be doing fun stuff anyway because it's homecoming week. So we'll have a table out there doing fun stuff. Come out and see me be a train monkey and play with the Rubik's Cube. It's lots of laughs. So, you know, in fact, I'm gonna see if I can arrange that some pizza brought up there too. So that'll give you a motivation.
Oh.
So y'all have a good weekend and we will see you.